Hi, my name is John Gulbranson and I'm the president of International Test Instruments. In this presentation I will talk about the history of PC buses from ISA to PCI Express. So it all started back in 1981 when IBM created the original IBM PC. That machine used a Intel 8088 CPU running at 4.77 megahertz, which resulted in the blazingly fast I/O bandwidth of 4 megabytes per second. The ISA standard, however, was created a few years later in 1984 when the PC-80, the improved PC, was created, which used the 8286 CPU. And that CPU uses a 16-bit data bus running at 8 megahertz for a total memory and I/O card bandwidth of 16 megabytes per second. There are two versions of the ISA card. The original 8-bit, which was used for the 8088 or original IBM PC. And you also have the 16-bit extended cards from the PC-80, which is technically only the ISA bus. The original one is not technically part of the ISA standard. Only the 16-bit one is actually spelled out in the standard, but commonly we call both of those card versions the ISA card. So depending on the actual CPU used, the 8088 or the 286, you can address either 1 meg or 16 meg of address range on the CPU bus and therefore also on the I/O card. Both of these CPUs support 64K of address space. One of the problems, of course, is that the ISA bus is not very fast. It was an old design from 1980, essentially, and after about 10 years, when Windows came along and other GUI-based operating systems, the I/O bandwidth was not enough to support the advanced graphics cards that started to come along. So the graphic cards manufacturers came together and through their group, the VESA group, Video Electronic Standards Association, created a VL bus or VESA local bus, which essentially was again a direct attachment of the graphics card and any other card, I/O card that you wanted to directly connect with high performance, and they connected it to the CPU memory bus again. And because the top of the line CPU at the time was the 486 CPU running at 33 megahertz, that was the bus standard for the VL local bus. And the problem, of course, with doing that is that they married it to the 486 CPU bus protocol, and when other CPUs came out, particularly the Pentium, it used a different bus protocol, and the VL bus was no longer an option. It simply didn't work. Later on, IBM tried to create a future-proof and CPU-independent alternative to the ISA bus as part of their MCA microchannel architecture design. And we'll talk about that bus and the VL bus in some future slides. This slide shows the original IBM PC-80 motherboard from 1984. This is the board that uses a 8286 CPU. And you can here see the two different slots. This is the legacy original PC slot, and this is the extended, you see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as ISA slots and therefore ISA boards. So in this slide behind me here, you see the pinout of the ISA bus connector. This is the hold connector for the that is spec'd as part of the 286 computer, and this part here is the original PC connector, the 8-bit. You have 8 data bits on this connector, and you have another 8 on this. So in total, you have 16 for the whole interface.
PCI Express. Einige werden sich jetzt fragen, warum erklärt ihr mir eine 10 Jahre alte Schnittstelle? Aber Tatsache ist, PCI Express war lange Zeit für viele Leute einfach nur der Slot, wo man die Grafikkarte reinsteckt. Und die Details haben eigentlich gar nicht so interessiert. Erst in den letzten Jahren, wo immer mehr PCI Express Geräte und Erweiterungsmöglichkeiten auf den Mainboards Einzug halten, wird es eigentlich immer wichtiger, was diese Schnittstelle eigentlich alles kann und macht. Und auch meine Mainboard-Reviews konzentrieren sich immer mehr darauf, welche Erweiterungsmöglichkeiten eigentlich über PCI Express geboten werden. Und viele Leser haben mich gefragt, was ist das eigentlich? Was ist eine PCI Express LAN? Was kann die? Wofür ist die da? Und deswegen versuche ich das heute nochmal ein bisschen zusammenzufassen. Erstmal als Kontrastprogramm, was PCI Express nicht ist, nämlich der Vorgänger PCI. Wir hatten bis vor 10 Jahren die primäre Schnittstelle für Erweiterungskarten. Seitdem versucht PCI Express das abzulösen, klappt aber immer noch nicht so ganz. Selbst für Skylake erscheinen wieder Mainboards, wo auch PCI drauf ist. Aber ich habe hier mal ein ganz altes mitgebracht, um das so ein bisschen zu verdeutlichen. Die Besonderheit bei PCI war, alle Slots hingen an einem gemeinsamen Bus und es waren auch relativ große Slots mit vielen parallelen Datenleitungen. Das heißt, wir haben hier 32 Datenleitungen, die gehen einmal komplett durch und jeder Slot hängt dran. Das war recht praktisch, weil man die Leistung auf beliebige Karten verteilen konnte. Nur war die Leistung irgendwann zu wenig und man konnte sie kaum steigern. Denn mit 32 parallelen Datenleitungen hat man das Problem, wenn die nicht alle genau gleich lang sind, genau gleich arbeiten, kommt am Ende nur noch Blödsinn raus. Die einzelnen Bits kommen nicht zum gleichen Zeitpunkt an über die vielen unterschiedlichen Wege und das Ganze macht das Mainboard-Layout sehr komplex. Deswegen hat man für den Nachfolger PCI Express ein komplett anderes Modell gewählt. In Hardware haben die beiden eigentlich gar nichts gemeinsam. Der Name ist zwar noch gleich und auch das Ansprechverhalten der Karten durch das Betriebssystem ist gleich. Das heißt, man musste Windows nicht umgestalten, um die neue Schnittstelle einzuführen. Aber mechanisch und elektrisch sind die komplett anders aufgebaut. Man sieht das hier schon so, die klassischen PCI Express Slots, die meisten werden sie zumindest kennen, gibt es zum Beispiel in unterschiedlichen Längen. Und das ist schon erst ein Hinweis darauf für das Grundkonzept, denn PCI Express arbeitet mit sogenannten Lanes. Wir haben nicht mehr einen Bus, wo ganz viele Datenleitungen versuchen parallel zu arbeiten, sondern wir haben eine einzelne Einheit, die nur aus einer Datenleitung vom PCI-Controller, zum Beispiel in der CPU, zum PCI-Endgerät, zum Beispiel auf der Steckkarte führt und eine zweite Datenleitung für den Datenverkehr in Gegenrichtung. Und diese beiden Leitungen arbeiten als eine Einheit, haben ihr eigenes Taktsignal und können sich nicht irgendwie gegenseitig stören, weil es ist halt nur eine Datenleitung, auf die die Daten hintereinander sequenziell kommen, statt dass man parallel mehrere Datenleitungen koordinieren muss. Wenn man bei PCI Express die Bandbreite aber über das Maß einer Lane hinaus steigern möchte, hat man auch die Möglichkeit, mehrere Lanes in einem Slot zusammenzufassen. Das heißt, wir haben hier zum Beispiel einen X4-Slot und hier einen X16-Slot, das ist der, den man typischerweise für Grafikkarten nutzt. Der ist logischerweise bei gleichem PCI Express Standard 16 mal so schnell wie der X1. Und auch hier ist das nicht etwa eine große parallele Schnittstelle, sondern wir haben hier wirklich 16 unabhängige Systeme zur Datenübertragung. Und wenn das eine mal ein bisschen anders arbeitet als die anderen, dann stört das nicht. Denn die Daten werden über jedes einzelne Lane als Pakete übertragen und erst die Pakete werden am Ende in der GPU wieder zusammengesetzt. Und dabei ist eigentlich vollkommen unabhängig, in welcher Reihenfolge die eingetroffen sind, solange sie jetzt nicht, ich sag mal, wirklich lange verzögert und zu spät kommen. Aber die genaue Timing ist nicht mehr wichtig und man hat somit wesentlich mehr Möglichkeiten, die Leiterbahn über das Mainboard zu führen. Die können auch mal ein bisschen unterschiedlich lang sein. Ein weiterer Vorteil dieser Lane-Bauweise sieht man schon, wenn man sich die Slots mal genauer anguckt. Und zwar fängt jeder PCI Express Slot ähnlich an. Wir haben hier diese etwas längere Kerbe, dann beginnt die kurze. Bei den großen Slots geht es dann halt einfach länger weiter. Aber der erste Abschnitt eines X16-Slots sieht genauso aus wie der X1-Slot. Und das ist auch absichtlich, denn man kann jede PCI Express-Karte auch in größeren Slots betreiben. Ich kann hier zum Beispiel meine X1-Karte auch nehmen und sie in den X16 stecken, wenn ich einen davon zu viel hatte. Und sie wird da genauso arbeiten wie in einem X1-Slot. Wesentlich flexibler, was die Nutzung von Slots also angeht. Es geht sogar umgekehrt. Einige Mainboard-Hersteller verbauen PCI Express Slots, die nach hinten hin offen sind. Das heißt, ich kann jetzt hier in einen mechanischen X4-Slot eine X16-Grafikkarte reinstecken. Und wie man vielleicht sieht, die Kontaktleiste der Grafikkarte ragt einfach nach hinten aus dem Slot heraus. Das heißt, sie kann 12 von ihren 16 Lanes gar nicht nutzen. Aber mit den ersten 4 wird sie genauso arbeiten wie sonst auch. Ein bisschen langsamer. Aber das Protokoll sieht vor, dass die Karten auch mit weniger Lanes zurechtkommen müssen. Also alles einfach und flexibel und super toll mit PCI Express. Dann würde ich jetzt garantiert kein Video drüber machen. Es kommen nämlich weitere Komplikationen hinzu. Genauso wie ich eine X16-Karte in einem X4-Slot betreiben kann, wenn sie mechanisch da reinpasst, oder eine X1-Karte in einem X16-Slot, spricht nämlich auch gar nichts dagegen, einen mechanischen X16-Slot mit deutlich weniger als 16 Lanes anzubinden. Und da kommen wir jetzt nämlich zu dem Dauerthema PCI Express Sharing und Umleitung von Lanes, um an irgendeiner anderen Stelle andere Hardware anzubinden. Ein aktuelles Beispiel habe ich euch mal mitgebracht. Ein brandneues Skylake Mainboard. Wer die Berichterstattung über die CPUs mitverfolgt hat, wird gehört haben, dass in der CPU ein PCI Express 3.0 Controller mit 16 Lanes sitzt. Wer sich dieses Board nun genauer anguckt, dem fallen 3 optisch hervorgehobene mechanische X16-Slots auf und die sind entsprechend der Folgen tatsächlich auch alle über die CPU angebunden. Wenn man jetzt kurz nachrechnet, 3x16 auf 1x16, das geht nicht auf. Und das ist typisch für moderne Mainboards. Und man kann immer sehr schön daran notieren, wenn man irgendwo diese rechteckigen Chips sieht, in dieser typischen, sehr regelmäßigen Anordnung, dann hat man quasi immer PCI Express Sharing auf dem Board. In diesem Fall sind 8 der 16 CPU-Lanes permanent mit der ersten Hälfte des obersten Slots verbunden. Die anderen 8 Lanes gehen aber erstmal zu diesen, ich nenne sie immer PCI Express Splitter. Und die haben die Möglichkeit, zwei ankommende Lanes je Chip in 2 verschiedene Richtungen weiterzuleiten. Entweder ebenfalls zum ersten Slot, dann erhält er alle 16 Lanes, oder aber sie leiten die 8 Lanes, die zu diesen 4 Instanzen gehen, zum zweiten Slot weiter. Dann haben wir hier also hier nur 8, aber hier auch 8 Lanes. Normalerweise kriegt der zweite gar keine. Der Trick dabei ist, das Ganze wird einmal beim Einschalten des Systems festgelegt. Das heißt, sobald ich eine Karte in diesem Slot hier montiert habe, selbst wenn sie gerade gar nichts zu tun hat, kriegt die erste Karte, meistens die Grafikkarte, immer nur 8 Lanes ab. In diesem Fall geht es sogar noch weiter. Sitzen nochmal 2 dieser schönen Chips. Die können von den 8 Lanes, die in diesem Slot weitergeleitet wurden, 4 Stück nehmen und noch einmal an diesen weiterleiten. Das heißt, obwohl dieses Mainboard garantiert von einigen Händlern mit 3x16 beworben wird, ist es eigentlich ein 8-4-4-Board. Einen kleinen Sonderfall des CPU-Lane-Sharings möchte ich an der Stelle auch erwähnen, weil er gerade auf besonders teuren Board anzutreffen ist. Und zwar gibt es nämlich einen Trick, sogenannte PCI Express Switch. Manchmal werden auch diese Umschalter, die ich gerade schon vorgestellt habe, als Switch bezeichnet. Der Begriff Schalter ist da im Englischen leider nicht ganz deutlich. Was ich hier meine, ist ein Switch im gleichen Sinne, wie es auch zum Beispiel bei Netzwerk-Switch verwendet wird. Das sind spezielle Chips, die nehmen die Lanes, die zum Beispiel von der CPU kommen, und bereiten diese intern auf. Das heißt, eigentlich ist der Chip mit 16 Lanes in diesem Fall an die CPU angebunden. Dieser Chip hat seinerseits 32 weitere Lanes, mit denen er andere Geräte anbinden kann. Bei derartigen Boards ist es also tatsächlich möglich, dass 2 Grafikkarten parallel mit 16 Lanes arbeiten und die können auch beide mit voller 16-Lane-Geschwindigkeit mit der CPU kommunizieren, nur halt nicht unbedingt zeitgleich. Es sei denn, es müssen zufällig genau die gleichen Daten von der CPU zu den Grafikkarten übertragen werden. Alternativ können sie auch untereinander mit der vollen Geschwindigkeit kommunizieren, ohne dass die CPU überhaupt belastet wird. Derartige Switches sind also eine Möglichkeit, die Leistung durchaus ein bisschen über das zu steigern, was die CPU selbst kann, und werden deswegen vor allem auf sehr teure Mainboards verbaut. Ich zeige das auch nochmal auf der Rückseite. Das kann man hier mit etwas Glück erkennen. Man hat hier also wirklich die Leiterbahnen, die von der CPU kommen. Die enden hier in diesem Bereich. Und von hier aus gehen deutlich mehr Leiterbahnen wieder los und zu den Lötkontakten der einzelnen Slots. Die gerade angesprochene Verteilung der CPU-Lanes mag jetzt einigen Leuten schon komplex erscheinen, aber eigentlich ist es relativ übersichtlich. Es gibt auf den meisten Boards die Möglichkeit, Lanes an weitere Slots umzuleiten. Auf einigen Boards gibt es halt noch die beschriebenen PCI Express Switch, die für effektiv mehr Lanes seitens der Endgeräte sorgen, als die CPU eigentlich bereitstellen kann. Das kann man in den Spezifikationen meistens ganz gut nachlesen. Unübersichtlich wird es nur bei der Sockel 2011 V3-Plattform, schlichtweg weil Intel da eine CPU anbietet, die weniger Lanes zur Verfügung stellt als die Top-Modelle der Plattform. Und das sorgt halt dafür, dass es alle Bandbreitenangaben in zweifacher Ausführung gibt, je nachdem, welche Chip man verbaut hat. Wirklich kompliziert wird es aber bei der zweiten Quelle von PCI-Express-Lanes auf modernen Mainboards. Und zwar hat nämlich auch der Chipsatz, der heutzutage nur noch aus einem Chip besteht und bei Intel PCA heißt, bei AMD FCH, ein PCI-Express-Controller eingebaut. Und der wird nicht nur genutzt, um Erweiterungsslots anzubinden, sondern auch diverse Zusatzcontroller. Zusätzliche SATA-Ports, USB 3.1, zum Teil auch zusätzliche 3.0 Ports, wie gehabt schon X1-Slots, X4-Slots und manchmal auch noch diverse weitere Sachen. Natürlich bei der neuen Generation sehr beliebt der M2-Port für schnelle SSDs. Da gibt es vielfältige Möglichkeiten. Auch Netzwerk oder einige Audiochips werden über PCI Express angebunden. Es sind also sehr, sehr viele Endgeräte, die in Frage kommen. Und diese Chipsätze haben auch nicht wirklich viele Lanes.
The computer currently has one IDE hard drive. This is connected to the primary IDE controller. It also has a single optical drive which is connected to the secondary IDE controller. I'm going to be adding a second IDE hard drive, and I'm going to add it as a slave device to the primary controller. I will be removing the original hard drive so I can show you what the hard drive looks like, and then also so we can reconfigure the jumpers. First I'll begin by removing the power lead, gripped onto the Molex connector, and then I pull it out of the device. Then I remove the ribbon cable. I grab the ribbon cable close to the connector and then pull straight out from the device. Each computer case manufacturer holds hard drives into the case differently. Some computer cases use a quick release rails. These will snap onto the hard drive so they slide into the case. Others will have a plastic or a metal removable cage that holds the hard drive in. This one happens to have a fixed cage. This is welded right to the case, and then it uses screws to hold the drive in place. I'll remove these screws so then I can slide the drive out of the case. With the screws removed, I can carefully move all the components out of the way and then slide the drive out of the case. Here's the IDE drive that I removed from the computer. Here we have the 4-pin Molex power connector. We have our 40-pin IDE controller. Has a keyed notch here so our data cable can only fit in one direction. And then our IDE device has jumper settings. Somewhere on the IDE drive there will be a legend or some indicators to indicate which jumper setting will specify the device as a slave or a master device or a cable select device. In this case, if we remove all jumpers, that would be a slave device. If we set the jumper to the far right, that would be a master or single drive. Or if we set it on the third jumper, that will indicate or enable the cable select feature. This device is going to be our master device. So we're going to set it as the far right jumper. So this white jumper right here is already in the proper location. So this device will be the master device. We're going to install this on the primary controller. This device is going to be our slave hard drive. We're going to add this to the primary controller. This device doesn't happen to have a legend on top, but if I turn it over, the bottom jumper settings are listed right on the board. So here we have CS. If we were going to have a cable select device, we would use the first jumper. If we were going to specify this as a slave device, we would use the second jumper, and then the master device would be the third jumper. In this case, this is going to be our slave device. We will move it over to the second jumper. So this device is now configured as our slave device. IDE devices support one of two settings. We can either set all devices as the master or slave device, or we can set both devices as cable select. If we use cable select technology, we're going to have to use a cable select supported cable. Here's an example of a cable select supported cable. A couple of items on a cable select cable. One of them will have a little notch out of it. So in this case, we have one of the wires has been punched out. We also have markers on the connectors to indicate which connector goes to which device. In this case, this one says sys board, so this plugs into the motherboard. The connector at the end of this cable supports drive 0, so we would put our drive 0 or our master device on the end of the cable. And then drive 1 or our slave device would go on the center connector. So if we're using cable select, we have to use a cable select cable. Some IDE cables like this one are what are called 40-wire cables. So there's 40 wires and a 40-pin connector. These are used for optical drives and legacy hard drives that only support ATA33 or less speeds. Newer drives that are ATA 66, 100, or 133 need to use an 80-wire cable. These still have a 40-pin connector, but they have twice as many wires to support faster speeds. You can use a 40-pin cable with an ATA 66, 100, or 133 device, but it won't run at the fastest speed. So it's recommended to use these cables, the 40-wire cables, only for optical drives, and the 80-wire cable for any newer hard drives. Remove the ribbon cables from the motherboard so we can get a good look at them. Under each of these IDE controllers we can see that this one says primary and this one says secondary. So we're going to connect our master and slave hard drives to the primary controller, and then our single optical drive will be on its own cable connected to the secondary controller. Whenever possible, you should separate hard drives and optical drives on separate controllers. In this case, we're going to put our hard drives on the primary controller and our optical drive on the secondary controller. You should also put your bootable drive that holds the operating system, you should configure that as the master device on the primary chain, and then any other hard drives or secondary hard drives should be configured as the slave device on the primary chain. Currently, our single optical drive is connected to the secondary controller. This cable is connected to our primary controller. This is what will attach our master and our slave hard drive. This is going to be our master device. We've got the jumper set correctly, so this is the master. Carefully insert this into the computer case and then install the case screws to hold it in place. Installed and fastened the case screws. Now I can connect the data ribbon cable. Generally you want the master device hooked to the end connector on the ribbon cable. This is our master device, so I'll connect the ribbon cable, and at this time I can also connect the power connector. Now I can install our slave device. This is our slave device. We've got the jumper settings set as slave, so I can carefully slide this into the computer case and then fasten the case screws. The hard drive screws are fastened. Now I can connect the secondary connector to our slave device. And then the second power connector. Here's a close-up to our setup. Here's our master device connected to the end of the cable. We have power connected, and then the secondary connector is connected to our slave device. This one also has power, and this cable is connected to our primary controller. With the hard drives installed, I can connect my monitor, keyboard, and mouse, power up the computer, and make sure that both drives are detected. Press the power button and boot the computer. As it boots, I can look at the BIOS splash screen, see if there's any indication that it found any devices. Press the pause break key to pause it. Here it indicates that it found a primary master device. It also found a primary slave device, and then a secondary master device. The delete key to enter the CMOS setup utility. Then I'll go into the standard CMOS features, and here we can see our current IDE setup. You can see our primary master device was auto-detected. It's a 40,000 megabyte or a 40 gig drive. Our primary slave device was auto-detected. It's a 19,996 megabyte or a 20 gigabyte hard drive. And then our IDE secondary master is an MSI CDRW. That's our optical drive. Looking at both the BIOS and the CMOS, it appears that the jumpers were set correctly and all devices were properly identified. So from here we could save our settings, the computer would restart, and then we could go into whatever operating system we're using, and now we would partition and format our hard drive to be able to use it.
The abbreviation SCSI is pronounced SCSI, and this stands for Small Computer Systems Interface. It was a method of connecting storage devices in, at that time, were small computer systems or personal computers, and it was one of the very first ways that we had standardized storage on our computer systems. We were able to do quite a bit with this. We could string a number of devices together. They could be hard drives, they could be optical storage devices, and we could put up to 16 devices on one of these SCSI chains using a single cable and a single SCSI controller. So you were able to just put one interface in your computer and simply hang off the back of that interface 16 different devices. Through the years, there have been a number of different kinds of SCSI formats. You may see it called fast SCSI, ultra SCSI, there's ultra wide SCSI, there's ultra 2 SCSI, and so on. All of these formats tend to be backwards compatible, but the best possible performance you're going to be would be to get a storage device and a controller that were using the same type of SCSI interface. Before USB came along, SCSI was really the standard for connecting our peripherals together. We would plug in printers, scanners, tape drives, CD-ROM drives, anything that needed an external connection. SCSI was the format that we were using. On these SCSI buses, we had different sizes. We had a narrow bus SCSI. Some SCSI was a wide bus. The narrow bus could plug in 8 devices that we could string onto an individual controller. The wide bus allowed us to have 16 different devices on a single controller. The part of SCSI that really makes it powerful is that the interface and the communication itself is very, very intelligent. It's very powerful. We're able to do a lot of different communication over that SCSI bus, and it was very simple to plug in. Even though we were able to control so many diverse kinds of devices, it was a single type of interface. We assign a number to it, and now we've got a SCSI connection on our computer. SCSI has been around for a very, very long time. But even today, especially in large server farms, we see SCSI interfaces for hard drive controllers, and especially on virtualized environments, we see a lot of SCSI being used. Even though it's not a physical SCSI connection, we're still using that SCSI standard of protocols to communicate over these virtualized systems. One particular piece of SCSI that was very important, especially early on in SCSI, was the termination. You could plug many devices in, but the last device had to have what we called a terminator on the end of the chain. That way, the SCSI communication knew exactly where the signal ended. Without a terminator, none of these devices would be able to operate properly. The newer SCSI devices tend to have these terminators built into the device, and you can enable or disable the terminator just by clicking a button. But the older devices needed a physical terminator that you would connect to the interface that was on back of the SCSI device. There are many different types of interfaces that you'll see for SCSI. They've changed quite a bit through the years. Here's an example of one. You can see this one happens to be an Ultra 3 SCSI connection, and you can see a PATA connection right next to it. They're almost the same size. The SCSI might be a little bit shorter. This is a view from above. If we were to look at it from the side, you can see the interface connector is a little bit different than the PATA or the SATA connections that we've used before. This SCSI connection has quite a number of pins associated with it. The cable that we would use to connect this would be something like this, where we would plug into the motherboard, and then there might be many different connections on that same cable where we could use all of these different SCSI devices and plug them all in at the same time. If we were to look closer, you can really see a lot of different pins being used. And on this particular SCSI connection, it was a higher bandwidth, so it needed a lot more pins to be able to communicate. But it may not be this type of connection that you would see with SCSI. Because they've changed so much through the years, you might see a DB25 connection that looks like a serial, or maybe even an older parallel connection. They all look very similar, but these are actually SCSI connections. You have to look very carefully to see the differences. Some connections are very clear that they're SCSI. This high density 50 pin connection has locks on the side of it that connect in. That's very, very exclusive to SCSI. And some of these higher density connections as well really make you see that very quickly that's a SCSI connection. There's nothing else that looks quite like those connectors. When you're physically connecting SCSI devices to the SCSI cable that you have, whether they are inside of a computer or outside of a computer, you have to give each one of them a completely unique number. This is called a SCSI ID. So on that single bus, on that single connection coming out of an interface of a computer, we would provide different IDs. For instance, if this was your boot disk, maybe we'll give that SCSI ID 0. If there's a floppy disk or a scanner or an optical device, we might assign that a number 2. If there's a CD-ROM, we might assign that with a SCSI ID of 3. There's also a concept within SCSI connections called a logical unit. So within each physical SCSI ID on that interface, you might have logical units inside of this. This was very common to see if you were plugging in an external SCSI storage device that had multiple hard drives inside of it. You would give the storage device itself a SCSI ID, and then there would be logical units assigned to the individual drives within that single physical device. You also see this quite a bit when you're working with virtualized systems. As I mentioned earlier, the signal that is at the very end of the SCSI bus has to be terminated. There might be a physical terminator, or it might be a termination functionality that's built into the hardware itself. If you ever see what we call SCSI attached devices that are serial attached SCSI, they don't have jumpers, they don't have terminators, they don't have settings. A lot of the more modern storage devices that we are plugging in over something called serial attached SCSI are completely automated in the way that they configure themselves on that SCSI bus. Here's an example of a legacy SCSI device. I think this is an optical device, but it could be a hard drive, it could be a scanner, it could be anything else. Generally, we see two different types of connectors on the back of the device. One of them generally is the connection going in. You can see it written on the back of the device, where we would plug in the in connection from our computer. If we had additional SCSI devices, we would use this out connection to keep the string going, to keep that daisy chain going throughout the connection. If this was the end of the line, if this really was the last device in this SCSI chain, this is where we would plug in the terminator. If this was a device that had the termination built in, there would probably be a connector on this device, or a button you could push to say this was the terminating place. And you can also see the SCSI ID number built right into this as well. There's little buttons that would allow you to change that SCSI ID. So when this device plugged in and communicated across the SCSI bus, everyone know that this device was SCSI ID number 6. Once you have everything plugged in, it looks a little like this, where you have a SCSI controller that might be ID 0. Here's SCSI ID 1, that's a hard disk. Here's another hard disk, and they're all chained together with different SCSI IDs, and at the end of the chain is a terminator. Usually these terminators even have a little light so you can see that they are active. Here's a picture of what a SCSI terminator might look like, so you can look at the back of your devices and see if you have one of those. That term daisy chain actually came from this idea of taking daisies and connecting them to each other, and you could wear them as bracelets or wear them on your head, and that same daisy chaining was how we came up with this idea of plugging in all of these devices one to the other to create that chain of devices. The back of the SCSI drive looks very similar to the back of any other hard drive. It's just using a very specialized SCSI connection on the back. Usually you have jumpers that can help you designate what the SCSI ID of this drive happens to be. And here's traditional power that you might find so that that drive can be powered up on the inside of your computer. If this was an external device, then you have external power. You usually have options for setting your SCSI IDs that we saw on the SCSI device earlier, and the interfaces for going in and out of that SCSI connection. The connection of the SCSI device on your motherboard looks very similar to PATA in that we've got a connection on the motherboard and multiple interfaces on SCSI. But of course, with PATA, we are limited to 2 individual devices, whereas with SCSI, especially the wide bus SCSI, I can connect up to 16 devices, and you would simply find the closest connector to you and plug it in. It doesn't matter where along this particular cable we plug in our SCSI device. The determination of how this device communicates is associated with the ID that you assign to the SCSI device. So you simply plug into the closest connector to you and plug in all of your different SCSI devices, make sure they have different SCSI IDs, and your SCSI communication is now complete. Once you follow those rules, SCSI is very simple to get running, and it's going to provide you with a lot of flexibility to plug in multiple storage devices. If you're working with a relatively new computer, then it most likely is using SATA connections to plug in the storage devices inside of that computer. Here's an example of one of those. This is a 256 gig solid state drive that is using SATA connections to be able to communicate. And we'll look closer at what that might look like. SATA stands for Serial AT Attachment, that AT attachment being that older AT computer, one of the original style computers, and we've kept the terminology through the years. Although the original computers are well beyond us, we have this serial AT attachment to have some comparison back to the older parallel AT attachment, or PATA. We have different standards for SATA. One of the original SATA versions was version 1.0. It ran at 1.5 gigabits per second. There's also another standard, which is the SATA revision 2.0, which is running at 3.0 gigabits per second. The latest SATA standard goes even faster than that. That's SATA revision 3.0 that runs at 6 gigabits per second. One thing you have to watch for is occasionally you will see people abbreviate 3 gigabits per second as 3G. We can sometimes confuse 3G with third generation. That's not really the case. I've been very careful here to show you SATA revision 1, SATA revision 2, and SATA revision 3, and then the speeds of those being 1.5 gigabits per second, 3 gigabits per second, and 6 gigabits per second. So if you're looking at standards for SATA, make sure you don't confuse any of that terminology. It can become confusing when you're dealing with different versions and different speeds, but as long as you synchronize those up, you shouldn't have a problem. One of the advantages that SATA brings to the table is that the connections are much smaller on the motherboard. You can see one of the older IDE or PATA connections on this motherboard, and this motherboard also has SATA connections, 1, 2, 3, 4, 5, 6 different SATA connections. If you were to look at these cables side by side, you'd really see the difference. PATA uses these larger ribbon connections. Here's the SATA connections, a much smaller connector on the motherboard and a much smaller cable that's being used to the storage device. So for the purposes of managing cables inside of your computer and making sure that the airflow is maintained through your computer, SATA has some distinct advantages. This is the back of a SATA drive, very similar to the PATA in that your interfaces are on this side. It's actually this very small interface is the SATA data connection. This larger interface is actually the power for SATA. You've also got these jumpers, and then you have an older traditional power connection. This drive was built for a computer that may be transitioning between PATA and SATA, and they gave you the option you could either plug in with the newer SATA power, or you could plug in with the older 4-pin Molex connector onto this drive. You would only choose one of those. You wouldn't need to plug both of those in. One of the advantages with SATA, however, is there's the capability on a number of drives to do hot swapping. You could unplug this drive while your system was powered up and plug it back in. That would be something you would not commonly do, and you would certainly want to take proper precautions when you were doing something like that, but it is part of the SATA standard. If we were to look at the top of the drive itself, it would give us that documentation of what we just saw with the power on one side, our serial connection, which is the data connection to our motherboard, the jumpers that are on the side, and there's a legacy power connection built in right into the documentation on the top of the drive. If your power supply had some of the newer SATA connections, you would simply plug the power connection into the SATA power, and you would plug your data cable into the SATA connector on the drive. If you have an older power supply, then you would plug it in very much like this picture shows, where you still have the same data connection, but you would use this legacy Molex power connector to make sure the drive was operational.
Inside every computer is a central processing unit, and inside every CPU are small components that carry out all the instructions for every program you run. These components include AND gates, which only allow electricity to flow to their output wire if all their input wires are on. The AND gates use tiny transistors to control the flow of electricity to the output wire. The electricity from another part of the computer flows in from the top and gets stopped at the first transistor unless its input wire is on. When that input wire turns on, it causes an electric field to form around a small piece of insulated metal. This electric field reaches out past the insulation and causes the properties of the semiconductor material below it to change, turning a small part of that semiconductor into a full conductor, bridging the gap for any electricity flowing in from the left and out to the right. The types of components you create from transistors are based upon how you wire their inputs and outputs together. If you chain them together so that the output of one flows to the input of the next, then you are creating an AND gate, where all the input wires must be on for the final output wire to be on. Inside the Scott CPU, you'll see a number of these AND gates scattered around, with some having more inputs than others. Another type of component that you'll come across is the OR gate, which is represented by this shape. Instead of chaining the output of each transistor to the input of the next, you instead run all the output wires to the same place, the output of the whole gate. In this way, if any of the transistors have their input wire on, then electricity flows straight through them to the gate's output. You'll also see a number of these OR gates scattered around the Scott CPU. By the way, the Scott CPU comes from the book But How Do It Know by John Scott, which is available at his website, buthowdoitknow.com. It includes a great explanation of how computers work for beginners, and John was kind enough to allow his CPU design to be used in this video. The other basic component you'll see in any CPU, including the Scott CPU, is the NOT gate. The NOT gate uses a transistor to divert the electricity already flowing to the output of the gate to a ground wire, effectively short-circuiting the output wire, turning the output of the gate off if the input wire is on. There are a number of these NOT gates inside the Scott CPU, not only in the locations seen here, but also inside the other components. For instance, the stepper component is just a particular combination of AND, OR, and NOT gates, where the output wires turn on in sequence each time the input wire to the stepper turns on. This input wire comes from another small component called the clock, where the output wires turn on and off again very quickly in a steady pattern. The only other component used in this part of the CPU is the selector, formed from another combination of AND, OR, and NOT gates that turn on one of several output wires depending upon what input wires are on at the moment. In another area of the CPU is the arithmetic logic unit, which includes more AND, OR, and NOT gates, along with the selector component that we just saw. There are a few other components in the ALU, like the exclusive OR and the NOR gate, but these are just made from the same OR gates we saw earlier, along with some AND and NOT gates. In other videos, we'll see how these components work together to process instructions sent to the CPU. This has been a brief look at what's inside the CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU.
Hello everyone, and welcome to this video. We're going to be talking today about what a register is. We're going to have a couple examples. I'm not going to explain all of them for lack of time, but the most basic function I will describe and define on those. So what is a register? A register is basically a group of flip-flops that are hooked together to hold certain aspects of data. So usually we're going to use in D flip-flops in the examples that we have here, but I guess that is what a register is. Now, what do we use a register for? A register, like we said, can be used for data storage, so we can use it to store data for further use. For instance, you can hold numbers in order to add them later, subtract them later, multiply them, or even display them on a LCD, for instance, if you have that kind of programming in your circuit or your processor. Data can also be transferred. Due to the fact that it is stored, it can be transferred from one register to another without losing the data. Now let's see a couple examples of registers in order to see what they do. These are one of the more simpler ones. We have, remember in these flip-flops, each bit requires a flip-flop, and in each flip-flop, in this case, Q follows D. Of course, in the shift to the left example, you can see that the first D follows Q, but that Q follows the last D. So it's really not that complicated of an issue. It's just Q will always become what D is. So D is the first state, and then you input it, and then Q outputs that. So we put in our first input there, and now we have the most significant bit to the least significant bit, which is X0. remember, the clock does not affect really whether it shifts from left to right. It is the hookups between the D's and the Q's here. Now let's look at this register. This register is a loadable 1-bit register in that it has an input, the DN. It has a load switch that says, do I want to load the old value, or do I want to load in the new value? If load is 0, then it's going to take that Q, which is this is the old value, the register with the old value, and it will take that and will say, okay, so that is the old value. Let's put the old value back into that register. Just keep cycling through. If it's 1, you're going to say, you know what? I kind of want this guy loaded in there, and that is going to be contained there, and it will wait for you to, it'll cycle back, and now it'll wait for you again to say, okay, do you want to load that new value back in again, or do you want to put an even newer value in? Now, once again, registers aren't the most complicated thing in the world, but they can get pretty complicated when you reach the capacity of a register file. So let's talk a little bit about that. A register file is an array, or basically kind of a string of registers together in one unit. So it can contain multiple numbers, and these numbers are going to do different things. They can be held together for math equations or for displays, as we said before. Here's an example. I couldn't really give you gate level just because this may become part of your final, and I don't want to give too much away there. But here we have a register file. We have 2 registers. Each register will hold a 4-bit, as we see from D0 to D3, it will hold a 4-bit number. And we see that the clocks are connected, and there is a write enable switch, which will allow it to be manipulated or moved or printed out on an LCD screen, or sorry, display. And those are the outputs. Now, generally, a register is going to be ALUs and muxes and other things are going to have registers because they also need to store data. But a register file may receive data that is stored in those functions and then be used to either be spit back into those functions, or it will be used in order to be shot to a display or just held there. For instance, if I were to have an ALU will have a register because it needs to hold a number. In the case of multiplication or something like that, it will need to have its own register file to store data. But let's say I want to take from the ALU and I want to spit into the register a 3, let's say, and I have a 6. So I would load a 3, and I would get a 3 from the ALU, and I would add the 2, 3 with the ALU, making a 6, and then I would say, okay, you know what, I want to load the lower register with a 6, and I want to load the higher register with the same value I had before, and I will we'll spit that number to the ALU and add that together. 3 plus 6 would be 9, and that way you can do even multiplication if you want. You can do addition, subtraction, all through the simple use of a register file and an ALU. You would obviously need a mux for a bridge point, but that's kind of besides the point. Just remember, registers are for holding data, 1 flip-flop per bit. They can contain several options, including write enable. They can include a load function, an enable input function, a shift enable, and it really depends on the way that you'll design them. But just remember that what they're for is storage, and what they're used for is data transfer and storage, and that they all need to be on the same clock, and that D will follow Q in most cases, And I guess the best way to learn about them is just kind of using them and playing with them in Xilinx, which you probably won't have a ton of time for, but in the labs you will be able to learn what a register does and a register file does in your final lab. So good luck to all of you, and I hope this has been of some help. Registers are definitely going to be a useful thing in your career, whether it be in software design or hardware, whatever. So try and pay attention to this part of the course.
MID is the processor register. In computer architecture, a processor register is a small amount of storage available as part of a CPU or other digital processor. Such registers are addressed by mechanisms other than main memory and can be accessed more quickly. Almost all computers, load store architecture, or not, load data from a larger memory into registers, where it is used for arithmetic, manipulated, or tested by some machine instruction. But cache is without doubt the most important thing you can have in your processor. It really does improve the performance of your system. Let me show you how it does it. Now we have a good little diagram here. There is processor, cache, cache controller and RAM. The cache can do something called reading ahead. Let me describe you what does that mean. Here in RAM, files are broken into little blocks, generally into 64 kilobytes blocks of RAM. Let's imagine we have opened a file, and we start reading it. The first thing the CPU does is to search for the file in cache, but of course the cache doesn't have it. That is called a miss. So in the second process the CPU goes to RAM and finds it in there, but it can bring over only one block at a time. So it grabs hold of that block, transfers it back to the CPU, and it starts working on it. And this is where the intelligence kicks in, because the cache controller makes a very good assumption that if I used that particular piece of code related to that file, I might need the rest of the code related to the file at some point very shortly in the future. So the cache controller grabs hold of the rest of the file and moves it to the cache. When indeed the CPU needs to find the rest of the information, it searches first the cache, and it finds it in there. That saves it from having to go to RAM at all. The main question here is why the CPU just doesn't go to RAM, and there is a very simple reason for this, because cache is much faster than RAM. Now you remember that blocks of code is moved from RAM to cache, and that's where the replacement policy decides where in the cache a copy of a particular entry of main memory will go. But when the cache is full, a replacement algorithm must choose which items to discard to make room for the new ones. If the replacement policy is free to choose any entry in the cache to hold the copy, the cache is called fully associative. At the other extreme, if each entry in main memory can go in just one place in the cache is direct mapped. Let's begin with fully associative mapping. Its approach is to store both memory address and data together in the cache. A fully associative cache requires the cache to be composed of associative memory holding both the memory address and the data for each cache line. The incoming memory address is simultaneously compared with all stored. If a match is found, the corresponding data is read out. Single words from anywhere within the main memory could be held in the cache, if the associative part of the cache is capable of holding a full address. In all organizations, the data can be more than one word, that is, a block of consecutive locations, to take advantage of spatial locality. In the figure, a line constitutes 4 words, each word being 4 bytes. The least significant part of the address selects the particular byte, the next part selects the word, and the remaining bits form the address compared to the address in the cache. The whole line can be transferred to and from the cache in one transaction if there are sufficient data paths between the main memory and the cache. With only one data word path, the words of the line have to be transferred in separate transactions. The fully associate mapping cache gives the greatest flexibility of holding combinations of blocks in the cache and minimum conflict for a given size cache, but is also the most expensive. It requires a replacement algorithm to select a block to remove upon a miss, and the algorithm must be implemented in hardware to maintain a high speed of operation. As we said, there is another mapping method called direct mapping. The fully associative cache is expensive to implement. In direct mapping, The cache consists of normal high-speed random access memory, and each location in the cache holds the data at an address in the cache given by the lower significant bits of the main memory address. This enables the block to be selected directly from the lower significant bits of the memory address. The remaining higher significant bits of the address are stored in the cache with the data to complete the identification of the cache data. Consider the example shown in the figure. The address from the processor is divided into two fields, a tag and index. The tag consists of the higher significant bits of the address, which are stored with the data. The index is the lower significant bits of the address used to address the cache. When the memory is referenced, the index is first used to access a word in the cache. Then the tag stored in the accessed word is read and compared with the tag in the address. If the two tags are the same, indicating that the word is the one required, access is made to the address cache word. However, if the tags are not the same, indicating that the required word is not in the cache, reference is made to the main memory to find it. For a memory read operation, the word is then transferred into the cache, where it is accessed. Here is the direct map cache with a line consisting of more than one word. The main memory address is composed of a tag, an index, and a word within a line. All the words within a line in the cache have the same stored tag. The index part to the address is used to access the cache, and the stored tag is compared with required tag address. For a read operation, if the tags are the same, the word within the block is selected for transfer to the processor. If the tags are not the same, the block containing the required word is first transferred to the cache. There is a third type of mapping called set associative mapping. Its scheme combines the simplicity of direct mapping with the flexibility of fully associative mapping. It is more practical than fully associative mapping, because the associative portion is limited to just a few slots that make up a set. The organization is shown in the figure. The cache is divided into sets of blocks. Each block in each set has a stored tag which, together with the index, completes the identification of the block. First, the index of the address from the processor is used to access the set. Then, comparators are used to compare all tags of the selected set with the incoming tag. If a match is found, the corresponding location is accessed. Otherwise, as before, an access to the main memory is made. The tag address bits are always chosen to be the most significant bits of the full address, the block address bits are the next significant bits, and the word address bits form the least significant bits, as this spreads out consecutive main memory blocks throughout consecutive sets in the cache. Notice that the association between the stored tags and the incoming tag is done using comparators, and can be shared for each associative search, and all the information, tags, and data can be stored in ordinary random access memory. The number of comparators required in the set associative cache is given by the number of blocks in a set, not the number of blocks in all, as in a fully associative memory. The set can be selected quickly, and all the blocks of the set can be read out simultaneously. After a tag has been identified, the corresponding block can be selected. The replacement algorithm for set associative mapping considers the lines in one set, as the choice of set is predetermined by the index in the address. Hence, with two blocks in each set, for example, only one additional bit is necessary in each set to identify the block to replace. Now let's talk a bit about the problems that occur. When a data is written to the cache, it must at some point be written to the RAM as well. The timing of this write is controlled by what is known as the write policy. In a write-through cache policy, every write to the cache causes a write to the RAM. Alternatively, in a write-back cache, writes are not immediately mirrored to the store. Instead, the cache tracks which of its locations have been written over. These locations are marked dirty. The data in these locations is written back to the RAM when those data are evicted from the cache. For this reason, a miss in a write-back cache will often require two memory accesses to service, one to retrieve the needed data, and one to write replaced data from the cache to the store. The probability that the required word is already in the cache depends upon the program and organization of the cache. Typically 70 to 90% of references will find their words in the cache, called a hit, but the rest is when a reference to the main memory is necessary, called a miss. The hit ratio of a cache describes how often a searched for item is actually found in the cache. More efficient replacement policies keep track of more usage information in order to improve the hit rate for a given cache size. The latency of a cache describes how long after requesting a desired item the cache can return that item when there is a hit. Faster replacement strategies typically keep track of less usage information. Or, in the case of direct mapped cache, no information at all, to reduce the amount of time required to update that information. The average memory reference time, as you can see, is a sum of the miss ratio multiplied with the time to make access to RAM, plus the time to reference the cache, if there is a hit, and last, some time for various secondary effects. If there is a hit in the cache, the first part becomes 0, and, as you can see, the memory reference time significantly drops. In other words, from top to bottom of the pyramid, every memory is a subset of the next in the hierarchy. The faster the memory is, the pricier it goes. But don't worry. Today's technology advances faster than it is expected, so prices are
RAM or random access memory is temporary memory, and is installed on the motherboard in the memory slots. A motherboard can have a various number of memory slots. The average motherboard will have between 2 and 4 of them. Memory slots come in different types, depending upon what type of RAM it accepts. For example, most motherboards have DIMM memory modules because it's the most common type to date. DIMM stands for Dual Inline Memory Module. A DIMM memory module has either 168, 184, or 240 pins. A DIMM is a dual inline module because it has 2 independent rows of these pins, one on each side. And DIMMs have a 64-bit data path. Another type of memory module is a SIMM. SIMM stands for Single Inline Memory Module. A SIMM is an older technology and has since been replaced by the much faster DIMM. A SIMM also has pins on both sides like a DIMM, but in a SIMM the pins are redundant, compared to a DIMM which are independent. A SIMM will either have 32 or 72 pins, and a 32-bit data path. Another type of memory module is called RIM, which stands for Rambus Inline Memory Module, which was developed by the company Rambus Inc. RIMs have 184 pins and look similar to a DIMM, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. Now the term 32 or 64-bit data path refers to the number of bits of data that are transferred in one cycle. The more bits that are transferred in one cycle, then the faster the computer will be. A single bit or 1 bit of data is the smallest form of data that the computer reads, because in the computing world, a computer only understands ones and zeros, which is represented by a single bit of data. Now there's also the term byte, and 8 bits is equal to 1 byte. So if a memory DIMM is rated to have a 64-bit data path, then that means that it has an 8-byte wide data path or bus, because 64 divided by 8 equals 8. And if a memory SIMM that is rated to have a 32-bit data path, then that means that it has a 4-byte wide bus, because 32 divided by 8 equals 4. So that's why DIMMs are faster than SIMMs. Now this information will be useful in an upcoming lesson on how we determine the exact bandwidth of memory modules. In Section 1, we talked about secondary memory, which is permanent storage. This dealt with hard drives. Now we'll talk about primary memory, or temporary storage. This is called RAM. RAM stands for Random Access Memory. In order for data or a program to run, it needs to be loaded into RAM first. So here is how it works. The data or program is stored on the hard drive. Then from the hard drive, it is loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the hard drive to compensate for low memory. So instead of data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on the computer. And by increasing the memory, all the data can be loaded into RAM without the need of constantly accessing the hard drive. And the result is a faster performing computer. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM is stored on the motherboard in modules called DIMMs. These DIMMs come in different memory sizes. Today, they range anywhere from 128 megs to 4 gigs of memory per DIMM or more. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors, and because it has capacitors, it has to be refreshed often. SRAM stands for synchronous RAM. This memory uses transistors and does not have to be refreshed, unlike DRAM. And because of this, it is much faster than DRAM, and it is also very expensive. An example of SRAM would be the memory cache level 1 and 2 that is used by the CPU. Another type of memory is called SDRAM, which stands for synchronous DRAM. This type of memory is what is used today in RAM DIMMs. The difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. SDRAM is rated at different speeds. For example, a stick of SDRAM could be labeled PC100. The 100 equals the speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC100, you multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC100 equals 800 megabytes per second. So an SDRAM module labeled PC133, you multiply 133 by 8 bytes, which equals 1066. So the total bandwidth for PC133 equals 1066 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock signal when compared to non-DDR RAM. Non-DDR or single data rate RAM uses only the rising edge of a signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which makes DDR twice as fast. DDR is also labeled differently than non-DDR RAM. Instead of including the clock speed in its name, like PC 133, where 133 equals the clock speed, DDR uses the total bandwidth instead. For example, a DDR DIMM labeled PC 2700, the 2700 is not the clock speed, but it's the actual total bandwidth. The clock speed for PC 2700 is 333 MHz. So 333 MHz times 8 bytes is rounded off to 2700 megabytes per second, which is where we get the name PC 2700. Another example is PC 3200. PC 3200 has a clock speed of 400 MHz, so 400 times 8 equals 3200, which is where we get the name PC 3200. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds, and it also uses less power than DDR. A DDR2 DIMM has 240 pins compared to 184 pins on DDR. Some examples of DDR2 are PC2 3200 and PC2 4200. And the latest RAM technology is called DDR3. DDR3 is twice as fast as DDR2, with a bandwidth of over 12,800 megabytes per second. Like DDR2, a DDR3 DIMM also has 240 pins, but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory, so you can't mix DDR1, 2, or 3 on the same motherboard. Some examples of DDR3 are PC3 8500 and PC3 12800. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 MHz, which was considerably faster than SDRAM, which ran at 133 MHz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 MHz, times the bus width, which was 2 bytes, you will get a total bandwidth of 1600 megabytes per second. RIM technology was designed to work with a continuous signal, which means that all the other memory slots on the motherboard must be used for RIMs to work properly. And if other RIMs are not available, then a user can install a CRIM or continuity RIM, which is basically a dummy RIM to ensure continuity in all the memory slots. To meet the higher demands of faster processors and memory controllers, a new technology was developed called dual channel mode. Dual-channel mode requires a pair of identical DIMMs installed on the motherboard, which allows the memory controller the ability to communicate with two DIMMs simultaneously, which increases the speed of accessing the memory. In order for dual channel to work, the motherboard must be equipped to work in dual channel mode, and the memory DIMMs must be identical to each other in speed, size, and features. Then the DIMMs must be inserted into the motherboard in a specific slot configuration in order to enable dual channel mode. Typically, the memory slots will be color-coded to help assist in identifying where the DIMMs should be inserted. For example, here we have some dual-channel memory slots. So in order for dual channel to work, you need to install a pair of identical DIMMs in the slots of the same color. In this case, we put a pair of DIMMs in the yellow slots. Some RAM modules have ECC, which stands for Error Correcting Code. And what this does is that it detects if the data was correctly processed by the memory module, and makes a correction if it needs to. You can tell if a RAM module has ECC by counting the number of memory chips on the module. In a standard non-ECC DIMM, it will have 8 memory chips, but in an ECC module, it will have 9 memory chips. Most RAM modules today are non-ECC, and this is because of the advance in technology that has minimized memory errors and has made non-ECC RAM more stable. Typically today, ECC memory is mostly used in servers because servers need to be up and running at all times, and using ECC memory is just an extra precaution to guard against any memory errors. memory slots. The average motherboard will have between 2 and 4 of them. Memory slots come in different types, depending upon what type of RAM it accepts. For example, most motherboards have DIMM memory modules because it's the most common type to date. DIMM stands for Dual Inline Memory Module. A DIMM memory module has either 168, 184, or 240 pins. A DIMM is a dual inline module because it has 2 independent rows of these pins, one on each side. And DIMMs have a 64-bit data path. Another type of memory module is a SIMM. SIMM stands for Single Inline Memory Module. A SIMM is an older technology and has since been replaced by the much faster DIMM. A SIMM also has pins on both sides like a DIMM, but in a SIMM, the pins are redundant, compared to a DIMM, which are independent. A SIMM will either have 32 or 72 pins, and a 32-bit data path. Another type of memory module is called RIM, which stands for Rambus Inline Memory Module, which was developed by the company Rambus Inc. RIMs have 184 pins and look similar to a DIMM, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. Now the term 32 or 64-bit data path refers to the number of bits of data that are transferred in one cycle. The more bits that are transferred in one cycle, then the faster the computer will be. A single bit or 1 bit of data is the smallest form of data that the computer reads, because in the computing world, a computer only understands ones and zeros, which is represented by a single bit of data. Now there's also the term byte, and 8 bits is equal to 1 byte. So if a memory DIMM is rated to have a 64-bit data path, then that means that it has an 8-byte wide data path, or bus, because 64 divided by 8 equals 8. And if a memory SIMM that is rated to have a 32-bit data path, then that means that it has a 4-byte wide bus, because 32 divided by 8 equals 4. So that's why DIMMs are faster than SIMMs. Now this information will be useful in an upcoming lesson on how we determine the exact bandwidth of memory modules. In Section 1, we talked about secondary memory, which is permanent storage. This dealt with hard drives. Now we'll talk about primary memory, or temporary storage. This is called RAM. RAM stands for Random Access Memory. In order for data or a program to run, it needs to be loaded into RAM first. So here is how it works. The data or program is stored on the hard drive. Then from the hard drive, it is loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the hard drive to compensate for low memory. So instead of data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on the computer. And by increasing the memory, all the data can be loaded into RAM without the need of constantly accessing the hard drive. And the result is a faster performing computer. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM is stored on the motherboard in modules called DIMMs. These DIMMs come in different memory sizes. Today, they range anywhere from 128 megs to 4 gigs of memory per DIMM or more. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors, and because it has capacitors, it has to be refreshed often. SRAM stands for synchronous RAM. This memory uses transistors and does not have to be refreshed, unlike DRAM. And because of this, it is much faster than DRAM, and it is also very expensive. An example of SRAM would be the memory cache level 1 and 2 that is used by the CPU. Another type of memory is called SDRAM, which stands for synchronous DRAM. This type of memory is what is used today in RAM DIMMs. The difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. SDRAM is rated at different speeds. For example, a stick of SDRAM could be labeled PC100. The 100 equals the speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC100, you multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC100 equals 800 megabytes per second. So an SDRAM module labeled PC133, you multiply 133 by 8 bytes, which equals 1066. So the total bandwidth for PC133 equals 1066 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock signal when compared to non-DDR RAM. Non-DDR or single data rate RAM uses only the rising edge of the signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which makes DDR twice as fast. DDR is also labeled differently than non-DDR RAM. Instead of including the clock speed in its name, like PC133, where 133 equals the clock speed, DDR uses the total bandwidth instead. For example, a DDR DIMM labeled PC2700. The 2700 is not the clock speed, but it's the actual total bandwidth. The clock speed for PC2700 is 333 megahertz. So 333 megahertz times 8 bytes is rounded off to 2700 megabytes per second, which is where we get the name PC2700. Another example is PC3200. PC3200 has a clock speed of 400 megahertz. So 400 times 8 equals 3200, which is where we get the name PC3200. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds, and it also uses less power than DDR. A DDR2 DIMM has 240 pins, compared to 184 pins on DDR. Some examples of DDR2 are PC2 3200 and PC2 4200. And the latest RAM technology is called DDR3. DDR3 is twice as fast as DDR2, with a bandwidth of over 12,800 megabytes per second. Like DDR2, a DDR3 DIMM also has 240 pins, but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory, so you can't mix DDR1, 2, or 3 on the same motherboard. Some examples of DDR3 are PC3 8500 and PC3 12800. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 MHz, which was considerably faster than SDRAM, which ran at 133 MHz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 MHz, times the bus width, which was 2 bytes, you will get a total bandwidth of 1600 megabytes per second. RIM technology was designed to work with a continuous signal, which means that all the other memory slots on the motherboard must be used for RIMs to work properly. And if other RIMs are not available, then a user can install a CRIM or continuity RIM, which is basically a dummy RIM to ensure continuity in all the memory slots. To meet the higher demands of faster processors and memory controllers, a new technology was developed called dual-channel mode. Dual-channel mode requires a pair of identical DIMMs installed on the motherboard, which allows the memory controller the ability to communicate with 2 DIMMs simultaneously, which increases the speed of accessing the memory. In order for dual channel to work, the motherboard must be equipped to work in dual channel mode, and the memory DIMMs must be identical to each other in speed, size, and features. Then the DIMMs must be inserted into the motherboard in a specific slot configuration in order to enable dual channel mode. Typically, the memory slots will be color-coded to help assist in identifying where the DIMMs should be inserted. For example, here we have some dual channel memory slots. So in order for dual channel to work, you need to install a pair of identical DIMMs in the slots of the same color. In this case, we put a pair of DIMMs in the yellow slots. Some RAM modules have ECC, which stands for Error Correcting Code. And what this does is that it detects if the data was correctly processed by the memory module, and makes a correction if it needs to. You can tell if a RAM module has ECC by counting the number of memory chips on the module. In a standard non-ECC DIMM, it will have 8 memory chips, but in an ECC module, it will have 9 memory chips. Most RAM modules today are non-ECC, and this is because of the advance in technology that has minimized memory errors and has made non-ECC RAM more stable. Typically today, ECC memory is mostly used in servers because servers need to be up and running at all times, and using ECC memory is just an